Hello APC Mechanics students in Unit 1 Kinematics, Class 10, Calculus Approach, Part 4. Section 1, Calculus the integral operator. In today's video, we're gonna check the operator, which is the integral, and this is considered as the reverse process of the derivative. The integral is the reverse process of derivative and usually named to be antiderivative. The integral or the antiderivative with respect to a variable x is denoted by, then this is the notation for the integral or the antiderivative. The linkage between variables of motion can be completed using integrals. Remember that previously we have introduced a linkage between variables of motion via the derivative. So we've said that we have the position, the velocity, the acceleration. We can go from the position to the velocity via a derivative. We can go from the velocity to the acceleration via a derivative. Now we can complete this linkage. So going from acceleration to velocity, that would require an antiderivative, which is the opposite of this, and this is known as an integral. And going from velocity to position, that would be represent it can be given by an antiderivative, which is integral. Now in the x direction, now we can relate quantities with each other, but remember that in physics our variables of motion are parameterized by time. So as I've mentioned that the position can be related to the velocity via an integral, and integrating over time, the position is given by the integral of the horizontal velocity plus a constant, and the velocity would be related to the acceleration by an integral plus a constant, where c is the constant of integration. Later on I'm gonna elaborate more about the constant. So dt would represent the differential variation of time. So dt is t final minus t initial, which is basically similar to delta t, but this variation is so small it tends to zero. For this reason it's represented by small d. Now that would be the indefinite integral operator, and c is the constant. In the y direction, similar relations can be introduced along the y direction. Then the vertical position would be the integral of vertical velocity, and vertical velocity would be the integral of vertical acceleration. Now, so far we have agreed on the notations and how variables of motion are linked to each other, as we have done in the derivatives. Now in section 2 we're gonna introduce the integral formula for a polynomial. Given the following polynomial, p of t is a t to the power of n, and here we're putting a condition that n is different than -1 and a is a constant. Then its integral with respect to time, t, is given by integral of, so here the integral is taking the polynomial function, which is a t to the power of n, and that would be t to the power of n plus 1 divided by n plus 1 plus a constant c, and let me explain it in the following way. So the integral can be understood by comparing it, or in contrast with the derivative. In the derivative we used to decrease the power of 1 by 1. Here we're increasing the power by 1. We used to multiply by the power. Here we're dividing by the power, where c is the constant of integration and n would be different than -1. The constant c can be determined using initial or final conditions, for example. So let me consider example 1. Given the following velocity time equations, find a corresponding position. All quantities are expressed in the SI. Now here notice the way that I pose the question, find a corresponding position, and this is important. Now in part A we have the velocity to be a linear function of time, and we need to find the position. In all of the previous examples we used to have, for example, the position, and we used to determine the velocity using a derivative. Now we can do it the other way around. We have the velocity and we can determine the position via the integral or the antiderivative. Then the horizontal position would be the integral of vx dt, which is the integral of 3t dt. Now we can drag the 3 out. That would be 3 integral of t dt. We increase the power by 1. That would be 1 plus 1 divided by 1 plus 1 plus the constant of integration, and that would be 3t to the power of 2 divided by 2 plus constant. Now what about the constant? Now if we consider the initial position at the instant t is equal to 0, that would be, now we have that x, this is x, is 3t squared over 2 plus c. Now x computed at t is equal to 0, that would be 3, 0 to the power of 2 over 2 plus c. That would be the initial position. So x at t is equal to 0 is the initial position, is equal to 0 plus c, and the constant c would be the initial position. It happens that whenever the function that we're dealing with is a polynomial function, then the constant of integration would be this variable at the initial instant, which is t is equal to 0. Now for part B, x would be the integral of 10t dt. We drag 10 out, we increase the power by 1, that would be 10t squared over 2 plus the constant of integration, which is, this is a polynomial, then that would be the variable of motion at the initial instant. So that would be 5t squared plus x0. Now for part C, x would be the integral of 3t dt. We can drag 3 out, that would be 3t to the power of 4 over 4 plus the constant, which is x0. Now Vx is 0. Whenever the function is 0, then its derivative would be 0 as well as its antiderivative. Okay, then in this case the position would be 0 as well. Now for part E, let me do that carefully. X would be the integral of 5 dt. We drag 5 out, that would be 5 integral of dt, and here the operator, it's not taking any function, which means that we have the unity, which is 1, and we cannot say that that would represent 0, because 0 would be a similar case of part D. Now the unity, which is 1, can be understood as t to the power of 0, since we're integrating over time, and now we can increase the power by 1 plus a constant which is related to this variable of motion, and that would be x0. That would be 5t plus x0. And for part F, that would be negative 20, the integral of t dt, and that would be negative 20t squared over 2 plus x0. We can divide by 2, and that would be negative 10 squared plus x0. And as you can notice that the integral increases the power, so linear becomes quadratic, linear becomes quadratic, cubic becomes quartic, 0 would remain 0, constant would become linear, and the linear would become quadratic. And why we've mentioned find a corresponding position, because all of these are not unique solutions unless we define what is meant by the initial position. So x0 remains constant. We know that in this case the constant represents the initial position, but we don't know the definite value of x0. For this reason, this is a solution and not the solution. Operations on integral section 3 consider u and v that are functions of time, distributivity over addition and subtraction. The integral is distributive over addition and subtraction. Then the integral of a function, which is an additive function between two functions u and v, would be the integral of u plus the integral of v. Similarly for subtraction. Now example 2, given the following velocity time equations, find a corresponding position. All quantities are expressed in SI. Here we can notice that for all four parts, v is given by operations between two polynomials, addition and subtraction, which is by itself a polynomial. Then the way to proceed is to integrate each one separately. Then for part A, x would be the integral of 10 minus 5t dt. Now let me do only the first one carefully. That would be the integral of 10 dt minus the integral of 5t dt. Now we can take the constants out. 10 integral of dt minus 5 integral of t dt. Now here we have 1, which is t to the power 0. Why I'm claiming it's t to the power 0 and not x to the power of 0, for example? Because we are integrating with respect to time. Then that would be 10t minus 5t squared over 2 plus a constant which is related to the variable of motion, and that would be x0, because these are polynomial functions. Now for part B, x would be the integral of 20t squared minus 30t cubed. So we increase the power by 1 and we divide by the final power. We increase the power by 1 and we divide by the power, and that would be x0. And here we can simplify, that would be 15 and that would be 2. Now here notice that this is a vertical velocity. We should integrate this. That would be t. So the vertical position y would be t plus t square over 2 plus t cube over 3 plus a constant, which is the vertical position computed at the initial instant considered to be time. Now for part D, y would be, let me also do that carefully, integral of a t plus b dt. Now we can distribute and take the coefficients out. That would be a integral of t dt plus b integral of dt, and that would be a t square over 2 plus bt plus y0. Okay. Now example 3, given the following acceleration time equations, find a corresponding velocity. All quantities are expressed in SI. In this case we have the acceleration, we need to determine the velocity, so we're going backward in variables of motion, and that can be done using antiderivative. Then ax, we need to determine vx, would be integral of 10 dt, and that would be a linear term 10t plus a constant which is related to vx computed at the initial instant 0, that would be vx0. And now for part B, vx is given by the integral of ax dt, which is the integral of 3t minus 5 dt, and that would be given by 3t square over 2 minus 5t plus the constant, which is this variable of motion computed at the initial instant. And we're gonna see that this trick only works whenever this function is a polynomial function. It breaks down whenever we're dealing, for example, with logarithmic, exponential, or trigonometric, as we shall see in unit 2, and that would be the answer. Now section 3 operations. Okay, we're still in the same section, but now, however, they're telling us, given the following velocity time equations, find the corresponding position. And why that? Because the solution is gonna be unique, simply because for each part they have provided for us enough information in order to determine or constrain the constant c. Let's start with part A. Now x of t would be the integral of 4t minus 8 plus a constant. Now here this constant, we can express it either at the final stage or at the intermediate stage, it doesn't matter, and that would be 2t square minus 8t plus c. In this case the constant would represent the initial position, for example, or we can determine this constant using this condition. We know that the position is 5 meters for t is equal to 1 second. Now we have replaced time by 1 on both sides. Now we know that x for t is equal to 1 second is given by 5 meters. That would be 5 is equal to 2 minus 8 plus c. Isolating c and solving, that would be c is equal to 11 meters. Why c is expressed as in meters? Because notice that here we're adding and subtracting functions to each other compared to x. So all of these terms have the unit of meters, then c would be in meters. And the unique solution would be given by 2t square minus 8t plus 11, and by itself this would represent the initial position. However, we've used another condition in order to determine that value. Now similarly for part B, we have enough information to determine the constant c. Now x would be the integral of 8t minus 10, which is 4t square minus 10t plus c. I repeat again, c can be represented either at the final answer or at the intermediate stage. Now we need to find the unique solution given this condition, so we can replace time by t on both members. That would be x computed at t is equal to 2 seconds, and here we replace time by 2. We know that this is given by 3, so we can replace it by 3, and in this case 3 is equal to 16 minus 20 plus c. Isolating and solving for c, we get that c is 7 meters. Why meters? Because all of these terms are added and subtracted, which means that they have the same dimension, which is meter, and the unique solution would be 40 square minus 10t plus 7. That would represent the initial position. However, we have used another condition, which is at t is equal to 2 seconds, in order to determine the value of c. Now section 4, bounded integral, definite integral. Let f be a function of time, and we define the capital F to be an integral, and due to the constant thing, be an integral of f over time. And in this case we can say that capital F is the integral of f of t dt plus c. Here, as I've mentioned, that c can be represented either at an intermediate stage or at the final answer. where c is the constant of integration. The above equality have infinite number of solutions, since the constant c has infinite values unless constrained by initial or final conditions. So the c can take any value, and this depends on the dynamics or the conditions of the system itself. And for this reason we say that this equation has infinite number of solutions, because we don't yet have any conditions in order to specify the unique value of c. This type of integrals is also known as indefinite integrals. Why indefinite? Because simply c has no definite value. We define the bounded integral or definite integral to be integral from a to b f of t dt would be the capital F computed at b minus capital F computed at a, where f is the indefinite integral of small f. So here let me say some stuff. A is the lower bound of this integral, b is the upper bound of this integral, and this would stands for the bounded or the definite integral, and let me explain more. Example 5, compute the following integrals. Okay, for part A, we need to compute the following integral bounded between -1 and 3. So the way to do that is to proceed with finding the integral of this function. Quadratic would be cubic, linear would be quadratic, constant would be linear. Computed between two different instants, -1 and 3. So now what we're gonna do is that we're gonna compute this function at 3. We're gonna compute this function also at -1, and we'll consider the difference between them. So but first, so as you can see here that we have computed this function at 3, and also have computed this function at -1, and we consider the difference between them. But first we proceed with the function with the upper bound minus the function with the lower bound, and if you plug that on the calculator, that would be 10. Now for part B, we're gonna do the same. We have a bounded integral between 2 and 4. So the way to do that is to integrate the function. Linear would give us quadratic, constant would give us a linear. Between two bounds, 4 and 2, 4 is the upper bound, 2 is the lower bound. So we always replace starting by the upper bound minus this function computed at the lower bound. We respect the order, and the answer would be 4. Now example 6, the speed v of an automobile moving on a straight road is given in meters per second as a function of time in seconds by the following equation. How far has the automobile traveled in the interval between t is equal to 0 and t is equal to 2 seconds? By how far, we're referring to the displacement or the distance. So in order to determine the position from the velocity, we need to consider the integral. And there is two ways to proceed with this examples. Let me now introduce the first method. The position is related to the speed by an integral. Then x would be in the integral of v dt, which is the integral of that function, and the result would be the integral plus the constant of integration. Now, okay, here we have simplified by 2. Now, how far corresponds for the distance, which is basically the magnitude of the displacement. Delta x is x2 minus x1. x2 would be computed at the later instant, which is 2 seconds, and x1 would be t is equal to 0. Now, for t is equal to 0, replace time by 0. That would be just simply the constant, because we know that this is the initial position related to x0. And x for t is equal to 2 seconds would be replacing time by 2, and that would be 16 plus 6. Now delta x would be x2 minus x1, which is 16 plus c. Then x2 in this case represents this, and x1 represents this. Then the difference would be simply 16 meters. So in this case we have enough information in order, we have enough information in order to determine delta x, which is the unique value. However, so then the distance covered in this time interval is 16 meters. However, this can be done using another method. Quantities related to variations can be defined as bounded integrals, known as definite integrals. So delta x can be given by the definite integral of v dt between two instants 0 and 2 seconds. And that would be integral from 0 to 2 of 4 plus 2t cubed. And now integrate the function, and we need to compute it between two different instants, 2 as an upper bound and 0 as a lower bound, and the answer would be simply 16 meters. And as you can see here that we have directly computed the displacement without referring to the intermediate steps, which is computing the position explicitly at two different instants, 2 seconds and 0 seconds. And by that, so the distance covered would be 16 meters. By that, we can say that section 5, variations as definite integrals, variations related to variables of motion like delta x, delta v can be defined in terms of bounded integrals. In the x direction, we know that the position is related to the horizontal velocity via an integral. So delta x would be the bounded integral between t1 and t2, such that t2 is a later instant and delta x would be representing x2 minus x1. x2 is computed at a later instant. And similarly for the horizontal velocity, delta vx would be the integral of ax dt between two bounds t1 and t2, such that t2 is a later instant and delta vx would be vx2 minus vx1, vx computed at t2 and vx computed at t1. Now also in the y direction we can claim similar relations. Delta y would be the bounded integral of vy dt, where t2 is a later instant, and delta vy would be the integral of the acceleration between t1 and t2, where t2 is a later instant, and delta vy would be vy2 minus vy1, vy computed at t2 minus vy computed at t1. Exercise 1. A ball of mass 2 kg is thrown vertically upward from the top of a building. The ball's velocity v as function of time is given by v is r minus st, where r is 5 and s is 10. So v in this case is given by 5 minus 10 t, and basically this is the vertical velocity. Why? Because we suppose that it's thrown vertically upward, then the velocity is only gonna vary along the y direction. If the ball reaches the ground at t is equal to 2 seconds, what is the height of the building? The best way to approach such exercises is by doing a small sketch, although it's gonna take time, but you can think about it saving time in order to get the result directly. So this is thrown upward. In this case, because the initial launch is upward, I'm gonna take the y direction to be up. I don't know if we're gonna use it, and that would be the origin. So it will take the following path and it will reach the ground. This is the building, and we need to determine this height. So the time lapse or the time of flight is given by 2 seconds, but we need to set the boundaries of the integral because we need a unique value. Now this is the initial position, which is yi, the point of launch, and this is the final position, yf. So if you're considering delta y to be yf minus yi, the displacement vector would be from the initial position to the final position, tail to head. Then the magnitude of this delta y would represent the height of the building, and this can be calculated using a definite integral delta y computed between 0, which is the point of launch. So here we suppose 0 seconds, to 2 seconds of the function 5 minus 10 t dt. So the answer of this integral would be 5t constant to linear to quadratic, 10 t square over 2 by 10, that would be 5 minus 5t square. This function computed between two bounds 0 and 2, we always start by the upper bound, which is 5 2 minus 5, 2 to the power of 2, minus the function computed at 0. So that would be 0, and that would be 10 minus 20, which is negative 10 meters. But remember, this is a displacement, can be positive or negative. We're interested in the height, so the correct answer would be B. Now exercise 2. An object moves along a straight line with a velocity v given as function of time t by the equation v of t is alpha t squared plus beta t plus gamma. Which of the following expressions represents delta x, the displacement of the object, as a function of time starting at a time t is equal to 0? So we need to determine the variation delta x given the velocity, and this can be introduced as a bounded integral. Then delta x would be the integral from 0 to v dt, and the thing is that they didn't define the upper bound for us, because the upper bound is not defined to be which instant. We're gonna keep it to be the value t, and that would be, so usually we use this trick a lot. So integral from 0 to t of alpha t square plus beta t plus gamma dt. Knowing that alpha, beta and gamma are constants of motion, that would be alpha t cube over 3 plus beta t square over 2 plus gamma t computed between 0, which is the lower bound, and the final undefined bound, which is t. And now we need to compute this solution at the upper bound minus the lower bound. The lower bound would be 0 because replacing t by 0 each one, that would be 0, so we can replace just by t, and that would be the same answer, alpha t cube over 3 plus beta t square over 2 plus gamma t, and the correct answer in this case would be D. Now an object of mass 10 kg starts from rest at a time t is equal to 0, so the initial velocity in this case is 0, and moves in a straight line for a time t positive. The object's velocity v as function of time is given by that, where v is in meter per second and t is in seconds. How far, which means we need to calculate delta x, does the object travel during the first 10 seconds of motion, and that would be the integral of v dt starting from 0 and ending at a defined final instant, which is 10 seconds. That would be the 0 to 10 2t plus 3t squared dt, and that would be 2t square over 2t square plus 3t cube over 3, that would be t cube, between 0 and 10. So we can ignore the 0 because this is a polynomial function. Then 10 to the power of 2 plus 10 to the power of 3, we always start by the upper bound. That would be 100 plus 1000, which is basically 1100, and the correct answer in this case is D. Now exercise 4, a plane starts at rest, so the initial speed is 0. On a straight runway, for the first 30 seconds, the plane's acceleration alpha is given as a function of time by the equation alpha is beta tau square, where beta is 1 over 90 meter per second to the power of 4, and t is in seconds. What is the plane's speed at t is equal to 30 seconds? So we need to determine the speed given the acceleration, and this can be done using integral. Now, because we need to determine the speed at a specific instant, which is t is equal to 30 seconds, now we can proceed in this exercise in two ways. Either we do it as an indefinite integral because we know the initial speed, or we do it as a definite integral. Now I'm gonna proceed with the, let's say, definite integral. So delta v would be integral from the initial instant, which is 0, to the final instant, which is 30, of beta tau squared dt. Now beta is 1 over 90, I'm gonna take it out. From 0 to 30 of t squared dt, that would be 1 over 90, so t cube over 30 computed between two bounds 0 and 30. We can ignore the 0 because t to the replacing t by 0, that would be 0, then that would be 1 over 90, 30 to the power of 3 divided by 3, sorry, that's 3, and that would be 100 meters per second. But remember, this is delta v, so v final minus v initial is 100 meters per second, and knowing that the initial speed is given by 0, so that would be 0, and in this case the final speed is 100 meters per second, and the correct answer is C. Now the velocity v in meter per second of an object moving in a straight line is given as a function of time by v is given by that, the total distance, and we have the boundaries of the integral. Then that would be delta x from 1 second to 2 seconds for the following function, and that would be 4t power 4 over 4, that would be t to the power of 4, plus 2t square over 2, that would be t square, between 1 and 2, and that would be, so we start with the upper bound, 2 to the power of 4 plus 2 to the power of 2 minus that computed at the lower bound, 1 to the power of 4 plus 1 to the power of 2. So that would be 16 plus 4 minus 2, which is basically 18 meters, and the correct answer in this case is B. Then that's it for me in this video, guys. See you soon in a new one.